Hello everyone, I hope you're doing well. In this video, we are going to solve problem 9.1 from chapter 9 of Fundamentals of Statistical and Thermal Physics by Reif. Let's see the problem statement and we'll dive directly into the solution. The statement says, consider a system consisting of two particles, each of which can be in any of the three quantum states of respective energies 0, E and 3E. Alright, the system is in contact with a heat reservoir at temperature capital T equals K beta whole inverse. Alright, so till that point we can see that we have a system of two particles here, and we can see what possible energies they could have. These are the three kinds of energy, 0, E and 3E, and we can see here the expression for its temperature is also given. So in part A, we have to calculate the partition functions if we assume that the particles are classical particles and distinguishable. Okay, they are classical and distinguishable particles. Considering that in mind, we have to calculate the partition function. In part B, what is the Z partition function? If the particles obey boson-Einstein statistics. Okay, those particles are known as bosons, which obey bosons Einstein statistics. They have used these symbols BE for boson Einstein statistics, and the particles which obey them are called the bosons. Okay, and we have to calculate the partition function by assuming that those particles are bosons. And in part C, we have to again calculate the partition function by assuming that those particles are fermions, that they obey Fermi-Dirac statistics. So the problem is really simple. What basically we need to calculate is partition function, and in all three parts we have to assume differently for the particles. In first part we'll consider them classical particles which are distinguishable. In second part we'll consider them as the bosons particles, and in part C we have to consider the particles to be fermions. All right, so we'll see how this will go. The last thing that I want to highlight in the question is that it is a system of two particles, not one particle. In previous chapters, we mostly considered a system of one particle, hence the formula for the partition function of a one particle is different, and the formula for a partition function of two particles would be different. That is why I'm just mentioning it. I'll point it out again when we'll be doing it. Okay, so let's quickly get started. So let's start writing the data. Okay, and we have three kinds of energy levels here. I'm calling the first energy level as E1 and it's 0. Okay, the second energy level E, and third energy level 3E. All right, now next we are given with temperature, an expression for temperature, that is K beta. K is the Boltzmann constant and whole power -1, and we can take it in the denominator. So it's simply T is equals to 1 over K beta. It's whole power -1 in the numerator, and when it's moved to the denominator, the exponent sign changes. Okay, while the magnitude doesn't change, but the exponent sign changes, and this is the temperature expression that we are given with. Here we can see that we have a system of two particles and three energy levels are there. So how we can calculate the partition function for a system of two particles? First of all, let's see the formula that we are going to use for a system of two particles. The partition function Z for a system of two particles is given by it is capital Z equals summation that runs for n1, which are the energy states of the first particle, n2, which is the energy state of the second particle. Okay, this is for the first particle and this is for the second particle. Then we have this exponential factor, the usual one, for the energies of the first particle multiplied by the energies factor, I mean I mean the exponential vector of the second particle, en2. All right, so how we calculate the partition function for a system of two particles is that we first find out all the possible states that this system could have. Okay, and that is not as straightforward as it was for a system of one particle. I'll elaborate that thing later, but for now let's see what it is. So what we'll do, we'll find out all the possible states this system could have, and then for all those states we'll do this thing, okay, and we'll add it up. Let me clarify, because that clarification is needed for me to make you people understand that how we are gonna how we are gonna find out all those possible states, okay. And that learning that method is really important because it's the only way to solve this problem. All right, and that is the trickiest part of this problem, that how we are going to calculate the possible states this system could have. After finding out all of the possible states this system could have, then we'll see that what is applicable for what kind of particles, okay, like what is applicable for bosons and what is applicable for fermions and what is for the classical particles. Okay, we'll do it later. First we need to learn how to determine those states. Okay, let's understand all those things, and let me clarify that whatever I'm gonna write here is not a part of neat solution. Okay, this is something that I wanna make you understand, and that is how we are gonna be able to solve this problem. Okay, that understanding that understanding is crucial. Okay, so what happens when we have a system of one particle? Okay, what would happen if we had a system of one particle? For example, we had energy levels 0e and 3e here, okay, and what possible states this particle could have in this system? One possible state is that it could be at 0 energy. Another possible state is that it is at E energy, and another possible state it is at 3e energy. A single particle could not be at more than one state. Okay, it could be at this state or this state or this state. It's not possible that this particle is both at E and 3e. That's not possible. Okay, that's for sure. It is either in this state or in this state or in this state at a time. All right, so we have these three different states this particle could be in. All right, and the partition function is the Boltzmann factor for each of the different states. Okay, so what we do is E1 by KT, then plus this is for the system of a single particle, and we put the value of E1, E2 and E3 here, which are the three different states here, and that's simply the partition function for a system of one particle. What happens when we have a system of two particles? The situation is not as straightforward as it is for one particle system, because now we have two particles. This is P1 and this is P2, and P1 could be at energy 0e and 3e, and P2 separately, independently, could be at 0e and 3e energy. All right, now this whole system is defined by P2 and P1 both. Okay, it is possible that P1 is at 0 energy and P2 is at 0 energy as well. It is also possible that P1 is at 0 energy and P2 is at 3 energy. It's possible that P1 is at E energy and P2 is at E energy. P1 is at 3E energy, P2 is at E energy, and so on. You can see that each of these combination is a different state for this system. So when we have a system of two particles, the pair matters. Okay, and all the different kinds of pairs of energies we get for P1 and P2 corresponds to different states this system could have. Okay, so here we had one particle, so there was no pairing needed at all because it was only one particle. But now there are two particles. One is wearing pink and the other is wearing red. It is a different combination. This is wearing green and this is wearing pink. This is a different combination. Just to show you that what I'm saying, that each of different combination represents a different state the system is in. Okay, because P1 and P2 can possibly at any energy level out of these three, and we are interested in knowing all the possible combinations of states this system could have in order to write the partition function, because the partition function is the summation of this Boltzmann factor for all the possible states the system could have. Okay, and for that purpose what we do, we find out for each state the Boltzmann factor. For the first particle, the energy we take for the first particle, which is this 0 by kT, multiplied by the Boltzmann factor of the second energy state the second particle have, which is 0 as well here, then plus, then for the second state we'll do it 0 by kT plus multiplied by e to the power minus 3e by kT, then plus sign. Then for the third state we'll do it, we'll multiply the Boltzmann factor of both the particles, and then we add up for all different. Okay, and this is how we'll find out the partition function for this system. Now you must be wondering that you can see that there could be many combinations possible. How we are going to calculate and determine all those combinations? And is there any systematic way? Yes, there is a systematic way. I'll show you people. And there's another thing that I want to tell you, that if P1 and P2 are taken as identical, then for a system of two particles, if for example there are three energy levels available, this rule that I'm going to tell you is only applicable for a system of two particles. Okay, and they are considered to be identical here. For the case where they are not identical, we can easily get information from this rule, but let us understand what this rule is for. It's for a system of two particles such that they are identical particles. Okay, so for a system of two particles, if for example three energy levels are there, so the possible combinations are given by adding from 3, then reducing the number until 1 is reached. So 3 plus 2 plus 1 is 6, so there will be 6 different combinations of states the system could have if the energy levels are 3 and particles are 2. Okay, and if there were 4 energy levels, for example 0e, 2e, 3e for example, then what are the possible combinations if there are two particles to occupy these energy levels? So to determine it, since 4 energy levels, so 4 plus 3 plus 2 plus 1, which is equals to 10, there will be 10 different combinations. This way you can know that different combinations, how much maximum you different combinations you will get. How you will determine it, I'll show it as well, but this tool will tell you that how many of them are there. Okay, so that you would not miss any. Everything will be clarified when we'll be solving the problem. Okay, everything will be clarified. Just notice the things you are getting. Okay, here you just need to notice that how we are gonna calculate the partition function. This is the formula. We'll determine all those combinations and we'll find out this product for each state and add them up. Okay, so in our case, since we have 3 energy levels there, okay, and there is a system of two particles, so the possible number of states we'll have is 3 plus 2 plus 1 equals 6. Okay, and they are considered as identical. Their permutation like is not considered. That point will be elaborated. Now let's do the neat work. Now whatever I'm gonna write is included in the neat work. Okay, that is something that I just told you people to understand the case. And now we are gonna do the neat work, and I am doing in the next sheet because it will require possible states. You can write it like that, and since we have 3 energy levels, we'll draw 3 lines. Okay, and this is for the first combination. Let us write the energy states here. It is E1 equals 0, it is E2 equals E, it is E3 equals 3E. And for each of the different states, I'm gonna draw these lines again and again to show and get the level diagram. and we predicted there are 6 different combinations or different states this system could have. So we'll draw 6 of them: 1, 2, 3, 4, 5, one more, 6. Okay, this is for the first combination, second combination, third, fourth, fifth, and sixth. Now let's see what these combinations are. Just follow the way I'm doing it and you can determine all of the possible combinations really easily. And since we have 2 particles, all right, so let's say there is one particle is there and the other is also there in the same state. Okay, there is another combination where both of these particles are in the second state. Then there is another combination where both of the particles are at the higher state. So these are the 3 combinations when both of them are the same state. Okay, now let's do the next, in which let's say one particle is at this position and the second is right above it. Let's say this is P1 particle and this is P2 particle. Now another combination could be when P1 is here and P2 is here, right above it. Okay, and the third combination could be when one of the particle P1 is here and P2 is at the higher level. Okay, now let me clarify you people the concept of identical particles and distinguishable particles. As I told you people that whatever configuration and number of possible states we are getting is for the identical particles. Okay, now what this means that you can see that P1 is here and P2 is here. There could be another combination where, let me draw this level diagram here, where let's say P2 is here and P1 is here, because this is another state if P1 and P2 could be distinguished. For example, this is Sarah and this is Amna, and there could be another combination where this is Amna and this is Sarah. This can only happen if both of them could be distinguished, if you can distinguish between them. But what if you can't distinguish between them? Both of them are Amna, so that doesn't mean that if it is here or here, you can't determine it. So that's the same state if they are identical particles. But if they are distinguishable particles, if you can distinguish between P1 and P2, then if P1 is above and P2 is below, that's a different state than this state. Okay, so that is why for these 3 states there will be 3 more different states in which we'll do the permutation of P1 and P2. Like its permutation has already been done. We wrote P2 here and P1 here, and for this P2 here, and in place of here P2 we'll write P1 here. This is a different state. And then we have this one here, and it could be like here is P2 and here we can set P1. Okay, this is how you are gonna find out all possible combinations. Alright, so it's 8 and 9 total states, all possible states. You must be wondering that why I didn't do it here for the first 3. It's because both of them are in same state. So if P1 and P2, both of them are in same state, if P2 is here and P1 is here, that doesn't make any difference to the state they are occupying, because both of them are occupying the zero energy state. But in these cases, P1 is occupying 0 state and P2 is occupying E state. Okay, so these energies are different, these states are different, so this permutation matters, but here the permutation doesn't make any difference. That is why we made another combination for each of this separate section. Okay, one permutation for this one, in which we just shifted the position of P1 and P2 here, and corresponding to this here, and corresponding to this here. Okay, so we got total of 9 different combinations or 9 different states. Now we have enough data and we can easily calculate the partition function for all of the parts. Let me make a line here so that you can distinguish. Okay, this is first state, second, third, fourth, 5, 6, 7, 8 and 9 different states. Now let's calculate the partition function. Hence, whenever you want to determine the possible states a system could have, what you have to do first of all is to see that what are the levels available. If there are 3 levels, make 3 lines here. If there are 4 levels, make 4 lines here. And then what you have to do, if it is a system of 2 particles, then calculate that what are the possible states you are gonna get if those particles are identical. Okay, so if there are 3 particles, so do 3 plus 2 plus 1 and you got 6. This is for the identical particles. Okay, then make the level diagrams 6 times here. Okay, after doing this, populate them in this rule the way I did. All right, and after doing it, see that what if you shift the positions and exchange the position of particles with each other, they'll give different state. Okay, so in this way you will get the total diagram. These are the major steps, and this understanding this step is really important. Now let's do the calculation for the part A properly now, because now we are ready enough for part A. Partition function for a classical particles is given by, for classical particles is given by capital Z equals, let's do this thing. Since they are classical particles, all of the states are possible. Okay, the particles can occupy all of these states. There is no forbidden state for classical particles. They can occupy all these possible states. Okay, so let's start doing it. First we'll write the Boltzmann factor for this first state, and we can see both of them have energy 0. Okay, energy of first particle is 0, energy of second particle is 0 as well. So e to the power 0 by kt multiplied by e to the power 0 by kt. This is for first particle, this is for second particle, plus Boltzmann factor for the first particle and the second particle, and its energy is E and its energy is E as well. You can write their energy right above them like that, 3E, 3E. Here it's 0, it's E, E, 3E. It will become really easy for you. 3E, 0, 0, E, E, 3E, 3E, 0. So now we can do it really easily. So it's E and E, both of them are E, so e to the power minus E by kt multiplied by e to the power minus E by kt. Plus sign for the third state, we can see both of them are in 3E state, so minus 3E by kt for first particle multiplied by minus 3E by kt for the second particle. Plus sign e to the power, fourth state is this, 0 for the first and E for the second. 0 for the first and E for the second particle, plus now it's time for the fifth, which is E for the first and 3E for the second. Once this diagram is in front of you, the solution is really quick. 0 for the first, 3E for the second, 3E for the second, plus 0 for the first, E for the second, E for the first, 3E for the second, 3E by kt, and last is 0 for the first and 3E for, okay, it's like 3E for the first and 0 for the second. Whether I'm writing it first or second, that doesn't matter, until e to the power 0. Whether I'm writing it first or this one first, that doesn't matter, because they are just getting multiplied and order of multiplication doesn't matter here. Now let's simplify it further and see what's here. So e to the power 0, it's 0 divided by kt is 0 actually, so e to the power 0 is 1, and this is 1, and e to the power 0 is 1 again, so 1 is 1 into 1, 1 into 1 is 1, plus it's e to the power minus e by kt, e to the power minus e by kt. Bases are same, powers will be added, and it will become double 2e by kt, since it's e by kt and minus e by kt minus e by kt. If you add them, it's minus 2e by kt simply, plus bases are same, powers will be added, minus 3e by kt minus 3e by kt. 3 plus 3 is 6, so it's minus 6e by kt. Okay, we'll put the value of t at the end. Next we have this, e to the power 0 is 1, and we are left with e to the power minus e by kt, plus it's e to the power minus e by kt, 3e by kt. So 3e and e is 4e, powers will be added. Okay, since the sign is same as well, minus minus is plus, so powers will be simply added, minus 4e by kt, plus it's e to the power 0, and e to the power 0 is 1, and it's e to the power minus 3e by kt. After this we have this one term, e to the power 0 is 1, e to the power minus e by kt, plus minus e by kt minus 3e by kt. So add them up, it's e to the power minus 4e by kt, plus e to the power, last one is minus 3e by kt. Now we can write all those terms together which have the same exponential factor in them. For example, we can see, first of all we'll write 1 because there is no 1 other than that, so it's simply 1. Then plus, is there any term with minus 2e by kt? We can see here there is no term like that, so we'll write e to the power minus 2e by kt as it is, because there is no other term to add. This is e to the power minus 6e by kt here, and yeah, there is no more term for this, so it's simply 6e by kt. It could not be solved further on. Plus we can see it's e to the power minus e by kt. Here is that term. This is also e to the power minus e by kt, so we can add them up. There are two of them, so 2e to the power minus e by kt. After that we have this 4e by kt thing, and there is one more of it, so plus 2e to the power minus 4e by kt, plus then we have e to the power minus 3e by kt, and there is one more term here, so they will be added, e to the power 2e to the power minus 3e by kt. Okay, this is the partition function. Now let's put the value of t right here, which is t equals 1 over k beta. So we can put right here, we can get the result in rough work. Kt equals k into, what is the value of t? 1 over k beta. K cancels out, and it means kt equals 1 over beta. Okay, and you can see here that t is in the denominator. Okay, so in place of t you will put 1 over beta, and beta will jump into the numerator because it's like e by kt kind of thing. So e divided by kt is 1 over beta, so beta will come here, so it's e beta. Okay, so wherever kt is written, you'll write beta in the numerator in place of kt. Alright, so I hope you got it. Now let's write it. Z equals 1 plus e to the power minus 2e beta. In place of kt division, all that, you write beta in the numerator of each term. So 6e beta plus 2e minus e beta plus 2e to the power minus 4e beta plus 2e to the power minus 3e beta. This is the partition function for classical particles which obey Maxwell-Boltzmann distribution or statistics. Okay, so this is the solution for part A. Now let's do the part B. For part B, the same figure will be used, so don't mess it up. You'll use it for part B as well as for part C. Okay, now in part B we are considering particles to be boson. If particles are bosons, then they are identical and can occupy any state. Okay, so what happens with bosons is that they are identical particles. That's the thing with bosons, and they can occupy any state. Okay, what happens with the classical particles is that they are distinguishable particles. We can assign positions to them and we can distinguish one electron from another electron, but in quantum mechanics we call particles to be bosons, and what they are is that they are identical but they can occupy any state. There is no forbidden thing in them. So since bosons are identical, that is why these three combinations are not valid here for bosons, because for bosons, since they are identical particles, p1 and p2 are same. Okay, p1 p2 here are same and same, so these are actually the same states. In case of bosons, since both of them are Amna, this is Amna and this is Amna, you can't distinguish between them, so this is Amna and this is Amna as well. Okay, there is no way to distinguish between them. That is why in case of bosons, we'll cancel out these permutation terms. Okay, and only the distinct states will be considered. All right, and this is what you will get for the identical particles using this rule as well. Okay, that is why I told you people that this is, they give you the possible states for the identical particles. It gives you the unique states only. So we'll find out the partition function considering these 6 states only for bosons, and z would be equals to, you'll do the same thing you did for the classical particles, but you will not consider the last 3 terms, like this term, this term and this term. Rest of all the terms will be same, so you can simply write them together till this point, and last 3 terms will not be written in case of bosons. So let's write them as we have already wrote them. So it's really easy. E to the power 0, e to the power 0 for first combination, e to the power minus e by kt, e to the power minus e by kt for second, e to the power minus 3e by kt, e to the power minus 3e by kt for third state, then e to the power 0 e to the power minus e by kt plus e to the power minus e by kt, e to the power minus 3e by kt plus e to the power 0 e to the power minus 3e by kt. Okay, so let's simplify. E to the power 0, e to the power 0 is 1 plus e to the power minus 2e by kt, powers will be added, plus e to the power minus 6e by kt plus e to the power minus e by kt. E to the power 0 is 1, so it's 1, e to the power minus 4e by kt plus e to the power minus 3e by kt. Okay, so z equals 1 plus, you can put the value of kt here, which is beta, so that you'll have beta in the numerator simply. So minus e beta plus e to the power minus 4 e beta and e to the power minus 3e beta, and there is no term here that could be added, so that is the final partition function for bosons. You can write it as zb. Okay, if you consider the particles to be boson. Now let's do the part C, when we are considering the particles to be fermions. If the particles are fermions, then they will be identical particles, and no two fermions, no two same fermions, no two identical fermions could be at same energy states, could be at same energy state. This is the Pauli exclusion principle, and this is what the fermions are obliged to follow. Okay, Fermi-Dirac statistics all the particles which follow Fermi Dirac statistics have this obligation that no two fermions could be at same energy state. Okay, two or more obviously. For example, if there are three fermions, no three fermions could be at same energy level all together at same time. Okay, they all have to be at different energy levels. And besides that, both of those fermions will be identical. If they are identical, then they could not be at same energy state. So let's see this diagram. Okay, this was already cancelled out because of the identical nature of the fermions as well as bosons. But for fermions, another thing that is here is that those states are forbidden in which both of the particles are in same energy level. Okay, this state is not possible for fermions to occupy. This is not possible, and this is not possible as well. Only those states in which they are at different energy levels will be applicable or allowed for the fermions to occupy. So for fermions, only three states are possible, and we can write ZB, and fermions, it's F. And this, and this. Okay, let's write the energy thing. For first particle is 0, second is E minus E by kt plus E and 3E minus E by kt into E minus 3E by kt, then plus sign. The third one 0 and it's 3E, e to the power 0 minus 3E by kt. Let's simplify. It's e to the power 0 is 1, it's e to the power minus E by kt plus the powers will be added. Base is same, this E is base and these are powers, they will be added, minus 4E by kt plus e to the power minus 3E by kt. E to the power 0 is 1, that is why. So this is the partition functions if the particles are fermions. This is the end of this solution. Okay. So thank God it's ended, and it was challenging for me to make all these things make sense for you people, because for some reason I was worried if I could convey all of the important things to you or not. Okay, so it's really important to understand things, and it will enable you to solve any kind of problem that comes to you. Now you are able to determine the possible energy states the system of two particles could have, whatever the energy levels are. Okay, whatever the number of energy levels are, you can easily do that now. And you can now know that what happens if they are classical particles. In classical particles, all permutations are possible. Okay, and the particles in classical physics are usually distinguishable. Okay, and that is why these permutations also exist, additional permutations also exist. But if they are bosons, these permutations do not exist, since they are identical. Amna here, Amna here, so no difference. I'm everywhere. No difference. And in case of fermions, they don't want to live together. Okay, they say that they want to live alone in their compartments. Okay, so yeah, that is it for this video. I hope you got it. We'll meet you in next video. Till then, take care. Goodbye. Like, share and subscribe.